Hello, everyone. So basically, today I will be teaching you week 12 content and its associated questions. Okay. So far, we have taught, I have taught you guys about the signals systems, its properties. Okay. So today I will be speaking and I'm waiting for some students to join. Just give me some few seconds. Week 12 have these properties. Okay. DTFT, jet transform, and block diagram representation. Okay. So myself, Annu. So today I will be covering the topics to be covered in this session are DTFT in the complex frequency domain, jet transform, properties of the region of convergence, such as ROC, then jet transform properties one, that is linearity, time shifting, time expansion, time reversal, jet scaling. Then jet transform properties 2, which is nothing but a conjugation and the convolution. Okay. So we have jet transform properties 3, which is causality and the stability. And jet transform for examples 1 and example 2 and some block diagram representation. The structure will be like this. First, it will be followed by concepts, then mathematical derivations, followed by problem statements with detailed solution. Okay. So we have the learning objectives. Okay. Understand the DTFT in the complex frequency domain. Grasp the significance of ROC for jet transforms. Master key properties of jet transform like linearity, shifting, scaling, etc. Then applying the knowledge to solve the standard problems. And then interpret the block diagrams in context of linear time invariant systems. Okay. So DTFT in the complex frequency domain is conceptual overview. Okay. The definition is followed by x of e power g omega. Okay. It's equal to summation of minus infinity to infinity x of n e power minus j omega. So DTFT is a continuous frequency of the real frequency variable omega. And when extended to complex plane, we write z is equal to e power j omega, which provides insight into frequency spectrum of discrete time signals. The key idea is we often analyze the DTFT on a unit circle, that is mod of z is equals to 1. But generalizing to the entire complex plane connects closely with the jet transform. Now we will see basically here the conceptual overview through MATLAB. So as you can see here, I will be introducing you with a practical example. Okay, the practical introduction to frequency domain analysis. This example shows how to perform and interpret the basic frequency domain signal analysis. The example discusses the advantages of using frequency domain versus time domain representation of a signal, which illustrate the basic principles or using simulated real data. Okay, so here, this is a magnitude response of the audio signal. So you can see here magnitude, phase response, then magnitude response of the audio signal, phase response of the audio signal. If you play, if you want, I can. So you can, I'm not sure whether the sound is shareable. I'm sharing it sound. See, this is audio signal. First, I'm running this, okay? So what is this? The frequency domain representation of a carrier signal carries information about signal's magnitude and phase at each frequency. This is why the output of FFT computation is complex. A complex number x has a real part and imaginary part xi. Okay, so the magnitude is computed as simply the root over xr square plus xi square, and the phase of x is computed as this particular the inverse tan inverse. So this is tan inverse, and you can use MATLAB, there's an apps and angle to respectively to get the magnitude and phase of a complex number. So let's see first read. Okay, now this was the content. Okay, this was the content. Now using FFT to observe only the frequency component. Then again, I'm running this part. So this is the resolution bandwidth, which is a showing acceleration power spectrum. Okay, it's the bandwidth of 50 0.625. Okay, and then we have the open loop and closed loop part. This is the frequency component. So using FFT, we are observing the frequency component. And if we see the magnitude and space vectors separately, so this is this. So magnitude is this, ranging from 0 to 20, and phase is ranging from 0 to 20. That is again from the radian here, and it is a dB. Okay. So that is the case. We also need to find the signal periodicity. The concept of periodicity was introduced in Fourier series. Okay. So let's see how we find the periodicity. So analyzing the cyclic behavior of the temperature in an office building. So what is that? Okay. So read this. The frequency domain representation of a signal allows you to observe the several characteristics of the signal that are either not easy to see, not visible at all when you look at the signal in the time domain. For instance, frequency domain analysis becomes useful when you are looking for cyclic behavior of a signal. Okay. Analyzing cyclic behavior of the temperature in an office building, consider set of temperature measurements in office building during the winter season. Measurements were taken every 30 minutes for about 16.5 weeks. Look at the time domain data with the time axis scale to weeks. Could there be any periodic behavior on this data? So let us see first data. So this is the temperature data. Okay. It is almost impossible to know if there is a cyclic behavior on the office temperatures by looking at the time domain signal. See. Okay. However, the cyclic behavior of temperature becomes evident if we look at the frequency domain representation. Obtain the frequency domain representation of the signal. If you plot the magnitude of FFT output with the frequency axis scale to cycles or week, okay, you can see that there are two spectral lines that clearly larger. Let me just put the charger. So it is almost impossible to know if there is a cyclic behavior if it is in a time domain. Okay, so let us see from the frequency domain representation. Obtain the frequency domain representation of the signal. If you plot the magnitude of FFT output with the frequency axis scale to cycles or week, okay, you can clearly see that there are two spectral lines that are clearly larger than any other frequency component. One spectral lines at 1 cycle per week. The other line lies at 7 cycles per week. This makes sense given the data comes from the temperature control building on 7-day calendar. The spectral line indicates the temperature follow a weekly cycle with the lower temperatures on weeklies. Let us see first. We are removing a DC component. Okay. See frequency cycles. So we are first classifying in the range. Okay. Once we are classifying the range, it is coming naturally how it is repeating. Okay. So it is repeating in different frequency range or different temperature range. That is the case. That is very good example, practical example of Fourier transform. Be it from continuous time Fourier transform, discrete time Fourier transform, but you have this. So measuring power. So I want to know, I want you to know about the power also. So the periodogram function computes the signal's FFT and normalizes the output to obtain the power spectral density, PSG, all power spectrum from which you can measure power. The PSD describes the power of a time signal is distributed with frequency. It has units of watts per hertz. You compute the power spectrum You compute the power spectrum by integrating each point of the PSD over the frequency interval at which that point is defined. That is over a resolution bandwidth of the PSD. Okay. So this periodogram function is used to compute for signal FFT and then normalizes the output to obtain the power spectral density. It will normalize the output to obtain power spectral density or power spectrum from which you can measure the power, because it is very important to get the power value of any signal. It determines how uh, long it can reach to a particular area. That is a matter. Okay. You compute the power spectrum by integrating each point of the PST or frequency interval at which that point is defined. You can read power values directly from the power spectrum without having to integrate over an interval. So measuring harmonics at the output of a non-linear power amplifier. So first we need to load the data, measure at the output of a power amplifier that has third order distortion of the form, where V naught is the output voltage, Vi is the input voltage. The data was captured with a sample rate of 3.6 kilohertz. So the input Vi consists of 60 hertz sinusoid with unity amplitude. Due to the nature of nonlinear distortion, you should expect the amplifier output to contain a DC component, a 60 hertz component, and the second and third harmonics at 120 and 180 hertz. So first we are loading this MATLAB file. Then it is a sample frequency. Then we are doing the NFFT, the number of FFT it should have, so the length it should give. Then power spectrum is computed when you pass a power flag input. So this is what the input function. So and now we have to see the plot analysis. So this is the plot. See carefully. The plot of a power spectrum shows 3 of the 4 expected peaks at DC 60 and 120 Hz. It also shows several more spurious peaks that must be caused by noise in the signal. Note that the 180 Hz harmonic is completely buried in the noise. So this is the measure the power of visible expected peaks. And peak power is a peak bandwidth, let's see. So peak powers, which is dB watt. Okay. Now, the most important application, improving power measurements for noisy signals. As seen on the plot above, the periodogram shows several frequency peaks that are not related to signal of interest at all. The spectrum looks noisy. The reason for this is that you only analyze one shot of realization of the noisy signal. Repeating the experiment several times and averaging would remove the spurious spectral peaks and yield more accurate power measurements. You can achieve this averaging using p-Welch. This function will take a large data vector, break into smaller segments of specified length, compute as many periodograms as there are segments, and average them. As number of available segments increases, the P-Wells function will lead a smoother power spectrum that is a less variance with the power values very close to the expected values. So if you load a larger observation consisting of 500 e power 3 points of the amplifier output and keeping the number of points used to perform the FFTs as 3600 so that the flow is equals to 138 FFTs are averaged to obtain the power spectrum. So this is the loading. So as seen on the plot, the P-Wells effectively remove all the spurious frequency peaks caused by the noise. The spectral component at 180 Hz that was buried in noise is now visible. So 180 Hz. So it is now visible. Okay. And this effectively yields more accurate power measurements. And it is leading more accurate power measurement. That's fine. So now measuring total average power and power over a frequency band. So measuring the total average power of a time domain signal is then easy and a common task. For the amplifier output signal, that is why the total average power is computed in the time domain as this is that will leave the same 8.1698. Okay, 8.1697. And in the frequency domain, the total power average computed as a sum of the power of all frequency components of the signal. The value of PWR1 consists of the sums of the frequency components available used in the power spectrum of the signal. So the values agree with the value PVR. So what does this theorem mean? It's a Parseval's energy theorem or Parseval power theorem that states that the Parseval energy theorem states that the Parseval power theorem states that the power or energy calculated in time domain is equal to the power and energy calculated in frequency domain. Okay, so far we have seen several outputs, and now going back to this. So DTFT and the relation to the jet transform. So DTFT is essentially the jet transform evaluated on a unit circle. So if we consider DTFT evaluation on a unit circle, it is actually a jet transform. Okay. So for sequence XNs, that's why the jet DTFT is there for only time domain signals. So jet transform is also for time domain signals. But in DTFT, we have some limitation of stability analysis or somewhat. So that's why when we call it in a unit circle, we do more stability analysis and we have a region of convergence kind of thing. So that comes in the jet transform. Okay. So xz is equals to minus infinity to infinity x of n z power minus n. And where z is equal to e power minus j omega n. So here also you can see e power minus j omega n. So substituting z is equal to e power plus j omega yields the DTFT. This connection is crucial for understanding the spectrum of signals and systems response. Now, if we talk about the poles, zeros, and the unit circle, so poles and zeros, that is a location in the complex plane where xz becomes infinite or zero. Okay. So what does this mean? So if it is becoming infinite, means if it is in a denominator. Okay. And if it is zero, means it is in a numerator. Okay. So the unit circle intersection is mod of z is equals to 1. So this is where DTFT is evaluated. So if we talk about magnitude and a phase, okay, so x of e power j omega is actually equals to mod of x of z, where z is equals to e power j omega. So mod of angle of x of e power j omega is actually the argument of x of z, where z is equals to e power j omega. So inside is what? Poles near or on the unit circle strongly influence the frequency response amplitude. The DTFT converges if summation of x power x of n less than infinity. In practice, many signals of interest are absolutely summable or of finite duration. So when signals are not absolutely summable, the DTFT might still be defined in a generalized sense. So what is the importance fact? This leads us to consider the ROC for the jet transform, which we will explore in the next topics. So there are some example problems which I will tell you along with the detailed solution. So problem is consists of given a discrete time signal, xn is equals to 1, 0. Okay. Defined from 0 to n minus 1. Otherwise it is 0. Find its DTFT and the requirements are use the definition of DTFT, simplify to the closed form and discuss the magnitude interface. Take your time, give me the answer. Okay, let me tell you the answer. So step by step evaluation. Write the DTFT definition. So we have written like this. So I don't know whether I'm teaching perfect or not, but whatever material I'm creating, it's best. Okay. So please look into it. Okay. I'm attaching all the PDFs there in the drive. So I hope you must have gone through these steps. Okay. So recognizing the final geometry series, simplify, magnitude and phase, and we have DTF definition. Okay. So we have recognized this one, and we finally found this magnitude and phase. So this is the problem statement 2. I want you to just to see this and try to tell me how to approach. Megha, I know for the subject we had 3 days, including me. So I understand that you may not be comfortable joining every session. In the 1 week, you have 3 sessions. That's why I have least attendance first time in NPTEL teaching. And that demotivates a lot. But still, if students are not there, I'm trying my best to provide the at least my slides that gives everything to you. Okay. So we have xn is equals to a power n um. For mod of a less than 1, where un is the unity unit function. Find the DTFT, which is x of e power j omega. Okay. So what is the first step? Again, we need to go through the steps. So if we find the infinite geometry series, the formula is 1 upon 1 minus r power n. Okay. So 1 upon 1 minus r. Sorry. So r is nothing but the ratio. Okay. So that is a e power minus j omega. So the convergence requires mod of a less than 1. On the unit circle, this holds if mod of a less than 1. The result is x of e power j omega is equals to 1 upon 1 minus a e power minus j. So there are properties of the region of convergence. So first definition is the set of z values, okay, for which the z transform xz converges. So the importance is it determines the system's stability, invertibility, and behavior. So typical shapes are ROC is often a ring in Z plane. So you have a mod of Z, okay, that is less than 1. If it is a ring in a Z plane, so typically that is the ROC. So before we move to this part, I would like to show you some Z transform example using MATLAB. So we have 3 functions, that's the 3 syntax, Z transform F, Z transform F, this one. So Z transform F defines the Z transform of F, okay, whatever the input is. By default, the independent variable is N and transformation variable is Z. So it, if F contains N, Z trans uses symmet bar. Okay, so let's see some examples. Symbolic expressions. So this is showing the symbolic expression. Symbol is N. So you can have an expression using MATLAB. Compute the Z transform of expression of M plus N. By default, the independent variable is N and the transformation variable is G. I want to see some examples. I think, sorry, examples are there. I think for Z transform, there is no example as of now. But yeah, fine. Now, you know, causal and anti-causal signals. What was that? Causal means a signal which is practical. That is, it is depending on the future output is depending on the past and present input. It is not depending on the future input. And the future input, do you think that it is practical? It is not. Okay. So causal and anti-causal sequences is causal sequence is 0 for n less than 0. Okay. So this is x of z. So ROC is outermost pole. As because in Laplace transform, what was the ROC? Rightmost side of the rightmost pole. And edge of n was 0 for less than 0, n less than 0. That was the criteria for causal signals. Okay, remember. I hope you remember. Whereas anti-causal signals lies for x of n 0 for n greater than equal to 0. Okay. Since in causal signal, this is 0,